Hey everyone, welcome back to my Calculus 1 series. In today's lesson we'll be going over tangent and secant lines and their application to velocity. So before we start the lesson, I quickly wanted to review the concept of slope. You've probably learned it in some pre-university course such as like Calculus 1, and you've probably touched up on it all the way through high school. As many of you know, the slope formula is pretty simple. It can be written as this. So I've written it in multiple ways here, but they all mean the same thing. So we commonly call the slope m because we use like the line y equals mx plus b, where m is the slope of the line. It can also be rewritten as like a difference between two coordinates. Let's say you're given two coordinate pairs where you have like x1 and y1, and then you're also given another coordinate pair where you have x2 and then y2. If we want to find the slope between these two coordinates, we can use a formula like this one to figure out the slope. In simple terms, all it is like a rise over run. So if we look at a line, we check how much it rises. Let's say we're looking at it between these 2 points. We check how much it rises and then check how much it runs. And then let's say this was a rise of 4 and a run of 3. Then we say the slope is 4 over 3. And lastly, we can use this delta sign. And basically, this is the delta sign. It just means like change in. So very similar concept, just the change in y divided by the change in x. So essentially it's this right here. Check how much is changed in the x coordinate, which would be here, and then we check how much is changed in the y coordinate here, and we divide the two. So we're going to start off with secant lines, and if you don't know what a secant line is yet, basically just a line that goes through a curve and intersects it at exactly 2 points. So just to give a quick visual example, let's say we have a graph such as this, and let's call this function right here in green y equals f of x. And basically a secant line, like the definition states, it will intersect the graph at exactly 2 points. So if we draw a line like this, we can see that it will have 2 points of intersections with the graph, one here and one here. Now, tangent lines are somewhat similar to secant lines. However, the only difference is that they will intersect a graph at exactly 1 point. So to give a visual as to what a tangent line will look like, we can pick a point, let's say here, and we can draw a line that will only touch this point once. So something like this. And as you can see from this line, it varies from what a secant looks like because it only intersects the graph at this 1 point. Now, as I mentioned in the intro, the concept of tangent lines and secant lines have immense applications to problems dealing with velocity. So the sample problem will go along the lines of something like this. The displacement of a particle moving back and forth along a straight line is given by the equation s equals 2 times the sine of pi times t plus 3 times the cosine of pi times t, where t is measured in seconds. And part A of the sample problem will ask us to find the average velocities during a bunch of given time periods. And then the follow-up question would be to estimate the instantaneous velocity of the particle at t equals 1. So the way I go about solving these problems is first, I find what the equation is that we will be dealing with. And the equation is right here. We know that this equation will graph to some sort of function. We don't quite know what it will look like, but we don't need to worry about what it will look like. We just need to know that this is a continuous function, and we somehow need to apply the concept of tangent lines and secant lines to figure out these rates of change. So I've zoomed out a little bit, but I will be continuing solving the problem down here, and we will go on with solving part A, and we'll solve part I of it. So the question asks us to find the average velocity during the time period 1, 1.1. One thing to note about this time period of 1, 1.1 is that this is not a coordinate pair. This is actually an interval. So this is an interval when the question stated that it was each time period. So this is when t equals 1, and this is when t equals 1.1. So if we go back to the beginning of the lesson, we know that to find the slope between two coordinates, we can use this formula right here. And we can use this formula and apply it to solve this problem, except the only thing that will change is the function is no longer called y, it's called s, and the x variable is called t now. So if we use that method to find the average velocity between these two times, it will look something like this. So now that we have this formula written out, all that's left to do is just plug in the variables. So s at 2 will be the function at the second coordinate, which is right here, and s of 1 will be the function at the first coordinate right here. Likewise, t of 2 will be 1.1, and t of 1 will be 1. So now time to just fill in the variables and solve for the value. So now that we've computed the answer, we know that this right here will be the average velocity during the first time period. Moving on to part 2 of the question, the solution is very similar. So I will just fast forward it, and you can just basically follow along with the steps. So as you can see, the solution for part 2 was very similar to the solution of part 1, and as you can conclude, the solution for part 3 will be almost identical to it. So there it is, there's the solution for the last part of part A. And now moving back up to the follow-up question, which was estimate the instantaneous velocity of the particle at t equals 1. One of the main changes that we can notice from this question to the previous one is that there's no longer this time period given, it's just at a single t value. So we don't have the tools to solve this problem yet, but further on in the chapter, we will figure out how to solve these types of questions. As of now, all we can do is estimate the instantaneous velocity. So if we look at all the time periods that were given, it was at 1.1, 1.01, 1.001, and we can see that we're slowly moving that time period closer and closer to 1 itself. And if we look at our results right here that we are getting, we are moving closer and closer to something like negative 6.3 centimeters per second. I personally think that a good estimate for the instantaneous velocity at t equals 1 would probably equal to negative 6.3 centimeters per second. So that's it for today, guys. It was a pretty short lesson. Hopefully you guys enjoyed it. If it helped you out at all, please leave a like and comment on what it helped you on. If you're new to the channel, please like, comment, and subscribe. It would be greatly appreciated. And yeah, I'll see you guys in the next one.